Okay, this is a quick tutorial walking you through the various types of titration analyses to determine the equivalence point of a titration, a potentiometric titration. So we're going to use a specific example of alkalinity since we're going to do that frequently in the 241 course, but this would work for any potentiometric titration. I'll also provide you this as a template, but it's important to know how the computations are made so that you can adjust them accordingly and input your own data as you collect it in the class. So the template will look like this. So I typically like to utilize tabs per sample, and I put my sample ID down here. Sometimes I put the date as well if I'm analyzing the same sample several times. Up in the top left corner, you have some generic inputs. So sample ID, collection analysis date, your specific titrant concentration. This is the standardized version, so this is really important that you know this to at least 4 significant digits. And then input your sample volume, which is, of course, highly dependent on the sample you're analyzing. This is a constant, this is a molecular weight of calcium carbonate, and this is unique to the alkalinity titration because we're going to use that value to compute alkalinity later. And so this video is going to walk you through 4 general methods to determine the equivalence point, and that's going to be part of your determination is figuring out which method is most precise and most accurate for use going forward. And so the 4 methods are the simple I estimate, which is analogous to looking at a color change with an indicator, something you would have done in general chemistry, and then we'll look at the first derivative, the second derivative, and then this thing called a Gran plot. And the Gran plot is related to this function, the Gran function f1, which I just have laid out here, which we will use that function and input that as we compute this column. And so the data that you have, and what I'd recommend in terms of the use of this thing is, of course, you're going to need to replace this data, and a convenient way to do that is to just make a duplicate of that spreadsheet so that you don't have to input or change the format of your template. So you can just right-click, choose Move or Copy, and then make sure you click this button, create a copy, and then click Move to End. And that's just going to generate a duplicate of that original spreadsheet. You can change the name here, change the values, input your own measured data, and then it will compute everything for you. And so I'm showing you data that is sort of generic collected alkalinity data. So we have what you'd collect in the lab. So you have the volume in terms of milliliters added of the titrant from the burette, and then we have the measured pH or the meter. And so this is what you would input yourself. If I make a plot of volume on the x-axis, dependent variable pH on the y-axis, you get the generic, this is a diprotic titration curve. Starting at higher pHs, that's due to the carbonate equilibrium, we reach this first equivalence volume, and then this buffer plateau, and then the second equivalence volume, that's for the bicarbonate to carbonic acid. And so this is the generic alkalinity titration curve that you'll be looking at for samples. But notice that these inflections, these changes in slope, aren't super obvious. And so if we're going to eyeball these, there's going to be certainly some error associated with this. So there's got to be a variety of ways to extract that. But in general chemistry, you would have either looked at the color change of an indicator, or if you collected this potentiometrically, you would have just looked at roughly the halfway point between sort of the flat regions where the slope changes the most quickly. So we're calling that the I estimate. And so to do that really generically and really simply, you can just kind of zoom in on your plot. For alkalinity titrations, we're really mostly interested, at least in terms of computing the alkalinity itself, we're looking at the second equivalence volume, because whatever we see as the total titrant added at the second equivalence volume, we can assume then there must be sort of 2 equivalents of that in the original amount of carbonate. And we'll talk about that more in class. So what I can do if I want to eyeball this is say, all right, well, roughly somewhere, this is a flat region, this is a flat region, so halfway between there, it's probably the closest data point is maybe this one. So I can sort of click on it and hover over it, and that gives me the XY points, so 4.80, comma 4.363. I can go over to my data here to the 4.80, and I can highlight that red, and that would be the equivalence volume that I would input as my I estimate, and that's as good as we can do. One note here is that we are conserving the correct number of significant digits in this computation because on the burette, we had 4.80. We have 3 digits that we can extract from the burette, this last digit being the one that we're least certain about, but it's the estimate between the gradation lines. This data is not captured in the most precise way because typically you want to design your titration such that the equivalence point of interest exceeds 10 milliliters to reach it. The reason for that is because if we have 10 milliliters here, notice then we've upped our significant digits, the ones we know, from 3 to 4. And so normally we're shooting for that. This example that I'm showing you only captures 3, which means it's not the ideal design for the highest degree of precision. Okay, so the next technique we want to employ is the first derivative of our titration plot. So really that's plotting the slope of the original titration curve as a function of volume. But there's a little bit of nuance here that we have to describe, and that's that when we're looking at the slope, which is really just the rise over run, so the change in pH, which is rise over change in run, so dpH dV in calculus notation like this, note that if I just sort of arbitrarily grab 2 points here and make a plot, so chart and then make a plot here, what I'm seeing here is if I compute the dpH dV, which is the change in pH over the change in volume, I'm really determining that between every set of 2 points. That's what we're doing in a spreadsheet computation of the derivative. And so when we replot the derivative curve, that dpH dV, that exact slope, is really the slope somewhere in the midpoint of this line, not at each of these individual points, because the line may change after that. And so when we're doing this by an Excel spreadsheet method, what we want to do before we compute the change in pH over change in volume is actually find the midpoint of these 2 volume points at every single volume change. And so that's what I have as this third column, Vmid, is the midpoint volume. And that's just simply calculated, if you look at this formula, as the addition of those 2 points divided by 2, which is really just telling you that's halfway between those 2 points. So that's this point between every set of points, because that's a more accurate representation of the volume at the slope that we're going to compute. So I'm going to go ahead and delete this, and now I'm going to compute this dpH dV parameter. So I'll say equals, and then I'm going to look at my pH, and I'll say I'm going to take and subtract each data point in sequence, and then divide that by the change in the volume, which will be this value subtracted by this value, close the parentheses. And so now we have the change in pH divided by the change in the original volume for each of these points. I can click and hold and drag to compute all the way down to the bottom here. And so what we've essentially computed there is the slope. That's the change in pH over change in volume, or the rise over run. And to plot this, I'm going to get this out of the way here, I can go to Insert, and I'm going to choose a chart here, and I'm actually going to choose I'm always going to choose scatter because I want the raw data, but I'm going to connect this with straight lines here just so that we can see the change illustrated more clearly. You never want to just plot the lines because that's disingenuous, because you don't know what the actual trend is supposed to be for the data. So I can connect the points, but the points are the most important thing to preserve here. So again, I'm going to go to Select Data, click Add. Now I'm going to choose my X values. In this case, my X I want to plot against that midpoint, remember, because that's the most accurate volume representation for that slope that we've computed. And then for the Y values, I'm going to plot this slope, the dpH dV parameter, and then I'll click OK, and then OK, and now I will have produced a plot that looks like this. We never use chart titles in chemistry figures, and then we always add axis titles. So I'm going to write this as dpH dV, and this is our V midpoint volume in milliliters. And so what we see here, if we compare these two plots together, they're over the same x-axis here. And so you notice that the slope change is greatest where we see this inflection. So that's where we see that first equivalence volume right at that point. and then the slope flattens out in this buffer region of the titration curve, so that's what we see here, and then it increases pretty rapidly again at the second equivalence volume. And so this becomes our estimate. So now this point, the point collected where we have the greatest change in slope, and so I can hover over that, that gives me 4.750. So I can go down to 4.750 and we get a little bit of a different estimate here, so 4.75. And notice, it's really important here that for both of these, the eyeballing or the first derivative, it's really critical that you have maximum numbers of data points where the slope changes the most. And that's always going to be your equivalence volume, because that's the region where you're removing the buffer from the system, where you're approaching the total amount of titrant added to completely neutralize whatever that species is that's in solution. And so there's no buffer region, so you get wild, rapid changes in pH as a function of small volumes of the titrant that's being added. And so if you miss this, if you go too quickly, then you'll end up having a big blank void space within those data points. These ones are pretty reasonably collected, but if there were a couple in the middle that were absent, then our estimate from the first derivative would not be as nice, nor would our estimate from our eyeballing method. Okay, so on to the second derivative plot. Second derivative is really just the slope change, or the derivative of this first derivative plot. And so what we'd expect is, you can see the slope here is negative because it's a decreasing, and then it switches abruptly to positive. And so if we take the derivative of this plot, which is the second derivative plot, what's nice is we start to see a change from positive to negative values, and they will intersect the x-axis, which will give us a little bit more clarity with exactly where these equivalents are. So I'll make that plot. And similarly, just as we've done before to find the midpoint volume, we're going to do the same thing and find the midpoint between the midpoint volumes. And so I just did that by taking the average. Oops, I meant to put this as plus. Taking the average of these 2 points, so that gives values that look like this. And for computing the second derivative here, I'm just going to take the difference in my first derivative, so this minus this, and then just like we've done before, now I'm going to use the difference in my midpoint volumes instead of the difference in my volume here. So take this value minus this value, close that, and drag this down. We get these values. Okay, so I can make a similar plot. This is the second derivative plot. And notice I have second derivative. I just wrote that out for convenience, but really we're plotting the d2pH, dv2 as a function of that midpoint volume here. So I can click on this. You can see these data went into making this plot. And notice what we're seeing here again is the slope of this plot. So the change in this plot as a function of that volume. And just as we mentioned before, we see an initial negative slope, and then we see this change to a positive slope, which corresponds to this inflection point in the first derivative plot. And so where it intercepts that x-axis, that is a good estimate of that first equivalence volume. Similarly, we can do that as this second equivalence volume. One handy thing for these second derivatives is in order to estimate where that intercept is, what I can do is just look at a simple plot of the 2 points that span that x-axis. So if I look here, hold this, I can find that's at the 4.8, 2.4 point. So I can go down here and find the 4.8, 2.4, and I can make that. And then I can look at this point down here and do the same thing. So if I look here, that's 4.7 minus 1.3, and so that's this next point. And one thing I can do is just make a new plot of this straight line here, and I have a plot that looks like this. So really all I'm doing are these 2 points are the same as these 2 points on exactly the same axis. I'm only plotting those 2 points. And so I can take these data and I can add a trend line to this, or a least squares fit, and I can go to more options, and what I get is a linear trend line between those 2 points, and I can set or display the equation on the chart, and what that will tell me is the equation of the line between those 2 points, and what we want to know is an estimate of that intercept. And so to do that, that's when y equals 0, right? And so to get that, I can either just punch these numbers into a calculator and compute it, or what I like to do and what I like to teach in analytical, since you're really becoming proficient with analysis and spreadsheets, is I can just compute the slope and the intercept and the x-intercept directly by using some of the commands here. So I can say equals slope, and now I can type in my known y's and x's. So remember, my known y's are going to be these 2 values here, and then my known x's are going to be these 2 values, and I can close that, and that gives me 37, and I can get more sig figs by just expanding this. That's exactly 37, and I can do the same thing with the intercept and grab the known y's, comma, known x's, close that, and now to get the x-intercept, that's when y equals 0. So that if we do the algebra and solve for x when y equals 0, then that's the same as just dividing the slope into the intercept, the absolute value of that. So I can say equals abs for absolute value. That just gets rid of that negative. And then I can take the intercept, divide by my slope here, close that, and that gives me this value here. So this is our estimate of the equivalence volume from the second derivative plot, and then doing a linear or a least squares fit regression between the 2 points that span the x-axis to get an estimate of where y equals 0. So I can click on this, I can copy it, I can go up here, and then I'm going to go to paste, and I'm just going to paste that value in directly. We're not preserving the correct number of significant digits here because I'm not reporting this yet. I'm going to use this to compute the alkalinity later, and that's what I'll use to compute an uncertainty, which will then constrain the number of digits that I actually keep. But for now, for simplicity, I'm just throwing them in there like that. Okay, so you can see that we're changing, right? Our initial eyeball was pretty close, 4.8. Our first derivative was slightly less, and our second derivative was slightly less. Now let's do this Gran plot method, which is something that you really haven't probably done before. So the Gran plot is based on this Gran function, which we're not going to go into great detail in this video, but we may talk about it in a classroom setting. But really, this comes from a 1980s article where you can pretty simply linearize the equation for pH as a function of the volume of the titrant added. And this all just falls out of the Nernst equation. Since a potentiometric titration, pH is directly related to the voltage of an electrode. And so you can do some algebra, you can do some simplification, and what you find is that the regions adjacent to the equivalence point, at least for a titration where you are titrating a weak base with, or a strong base with a strong acid like we are in an alkalinity titration, when we're just past the equivalence point, we get this linearized form of the expression. So we call this the Gran function. And the idea is that if you take your titration data and you plot this Gran function as well, when the line becomes straight, it becomes a really nice estimate or proxy for the equivalence volume. And I'll tell you why that's beneficial. But first, let's compute it. So to compute it, all we're going to do is take this first cell under Gran, and we're going to type in this equation. So V0 or V sub 0, that's the initial volume of our sample. So that's this 50 mils. So I'm going to say 50, and then I'm going to click F4 on a keyboard, and all that does is put dollar signs here, and the dollar signs keep that cell fixed because that's a constant. So when I drag down later, it doesn't also drag down here and give me erroneous numbers. So I'm going to choose add, and now plus V, V being the volume of the titrant that's added. And I'm not going to constrain this value because I want that to change as I drag that down. I'm going to close that parenthesis, and then I'm going to multiply by 10, and then raise that with the caret symbol and do pH in parentheses, and I'll do negative pH, and then I'll close that. And this will compute this Gran function, or this F1, and I can click and drag this down, and we'll get a bunch of these numbers. So this is the linearized expression as we're close to the midpoint, or the equivalence point. So let me show you what this plot looks like. So go to Insert, and I chose a scatter plot again. For x values, I'm going to take the original volume here, not the midpoint volumes, and then I'm going to plot that against this Gran function that we just computed. So grab that, I'll click OK, and we have this plot. This is an error of mine. So we get something that looks like this. So let me drag this down. We got lots of plots here. So this plot's pretty cool. So what is it telling us? Well, you can kind of see some distinct regions. Let's label this. So we have our, I'll just call this F1. That's our Gran function. This is actually in units volume. And now we have this as, we'll just say volume. And what we see is that we kind of have this flat line here, which corresponds to this region of the titration curve. But as we move past that second equivalence volume, so as we move just past these values, then we start to get this linearized form, and that's because the equation is specifically linearized to the conditions in solution when you have a strong acid titrating a base just past or at the equivalence volume. So the cool part about the Gran function and the Gran plot is that none of this data up here, none of it matters. So from the initial reading all the way to the equivalence point, none of that is used in the analysis, which means that if you collect really poor data at these equivalence points, doesn't matter. The Gran plot doesn't care because it's using the tail out here as a linearized form, this portion, to extrapolate back to the equivalence volume. And it turns out this is the most precise way to compute, often, not always, but often, simply because it doesn't rely on that the equilibration challenges of the pH electrode when you have wild swings in pH near the equivalence volume. Because remember, when you're doing this titration, you're adding tiny drops, maybe half drops of your titrant, and you're seeing half to maybe even full pH unit changes in your data. That's an order of magnitude change in concentration and proton concentration in the solution or hydroxide concentration that your pH electrode needs to respond to. And it can't do that very quickly. And so if you end up going too quickly and the equilibration doesn't last, or you just don't collect enough data points in this region, then you know, if you're doing this by eyeball or first or second derivative, your data suffers for that, or your equivalence point determination suffers for that. But for Gran, doesn't matter because it's everything past that second equivalence that we're interested in. So what you want to do for the Gran analysis then is we want to replot this, but we want to plot only the linear section. So how do we know that? Well, you can just look at this by eye, and I can see that probably this data point all the way up through this data point, that looks pretty straight to me. So I'm just going to click this data point, and you'll get pretty good at checking this on your own. So that's data point 4.90 in volume. So I'm going to go to here, and I'm actually just going to highlight this whole region, and I'm just going to fill this with some sort of light color because that's the region, that's all of these straight linearized data points out here that I want to replot. And I can just plot them on this same graph. So I can go up to chart design, select data, and I can add another series here. And I'm going to choose now my x values only in the highlighted region, only the ones I determined as linear. And now I'm going to take the Gran function as my y, but also only in that linear portion. And so now I have this orange plot, which are identical data points. I've just now parsed them on the plot. So if I click on my plot here, and note I'm highlighting just the orange because it's pulling up just this set of data. Now I can go and add a trend line to this, choose more options, display equation, and the r-squared value on the chart. Okay, so what's this telling me? Well, it's telling me this is the equation of this line. It should be linear because that's by design. That's based on sort of first principles chemistry. And it's telling me how well that least squares regression fits that data with 0.9994 as the r-squared value. So that's really good. Typically, you're aiming for above 2 nines. The other general rule of thumb as you're doing a Gran plot analysis in your titration is you want at least 5 or 6 data points here, ideally around 10, to get a good representation of the behavior out here. So you don't want to do this fit just with a few data points down here. And that's important if we look at where we are in titration space, look at these volumes, or look at these pHs. The equivalence point was, by eyeball, roughly at a pH of 4.3. And so that means you could have stopped your titration there if these were your estimates, or if these were the way that you were going to determine equivalence volume. But for a Gran titration, we want to go significantly past where that equivalence point is in that titration. And so often I suggest going out to around a pH of 3 or 3.2, really targeting about 5 to 10 points in this linear region of the plot so that you get a good fit and you get a good estimate. So similarly, like I did before, I can compute my slope-intercept and the x-intercept. So it's the x-intercept here that will give us an estimate of the equivalence volume. And so I'm going to go ahead and just copy these points down here, and I will say equals for my slope. Oops. Now I'll choose my known y's, and that's my Gran function only in the region of linearity, and then I'll choose volume as my x, and then equals intercept, and do the same thing here for known y's, and then the known x's. And then, similarly, I can just grab this because the computation is the same for the x-intercept. It's the absolute value of that intercept divided by the slope. So that gives me 4.711. So I can scroll back up here, paste this in as a value, and now we have an even better estimate of that equivalence volume. And you can see the trend here, where we have sort of an overestimate by I, a slight overestimate by first derivative. We're getting a little bit closer by second, and Gran plot we get typically the most precise. Okay, so now you can compute the alkalinity. I'm not going to do that for you because I think that's something that you can determine on your own based on the stoichiometry of the reaction here and the known equivalence volumes that you've computed. And then, of course, you would want to do this several times so that you could compute an average, a standard deviation, and a relative standard deviation. And these values compared with other classmates' values or known values will allow you to make assertions about things like the precision of each of these analyses, the precision of your experimental method, the accuracy of your method, etc. And I would do that just by taking this trial 1 data and probably just copying the first few lines so that the equations or formulas are preserved. Go straight over here, paste that in, change this to trial 2, and now as I collect volume pH data, I will just update these values, and then continue them, and then just drag my functions, because the functions are unchanging for each of these. Make new plots, do my analysis, punch my values in, and I'll be able to compute for all of these different methods what the alkalinity is, the mean standard deviation, the relative standard deviation.